Hi guys, so today we're going to be going over fine-grained synchronization, and once again we're working from this textbook. I realized that in my previous two videos I actually got the title wrong. It's the art of multiprocessor programming, not of multiprocessing, and it's by these people over here. So let's begin. Fine-grained synchronization. We spoke about coarse-grained synchronization where you have a single lock for the entire linked list. However, with this one, we noticed that there was a problem. We're not taking full advantage of the possibilities with concurrency, right? We realized we were kind of losing out on efficiency, so to speak. And so a better method would actually be to, instead of having a single lock for the entire linked list, we lock the individual nodes of the linked list. So how exactly would this work? So the way you would go about it is the a given thread, let's say thread A, would go and it would go through the entire linked list, locking nodes as it goes. So let's just say we have this linked list. It would lock this one, then it would lock this one, let go here, lock this one, then let go there. That's basically how it's going to look. And it's going to make use of, for adding, is going to make use of what we call hand over hand locking. You saw that before it let go of this one, it actually first acquired the lock over here, right? And this is called hand over hand locking, or it's called hand over hand locking or lock coupling. Lock coupling. And we'll get into this more as when you guys actually see the code. So let's just have a look at the code and see what's happening over here. So once again, as usual, we put the key into a variable and then we lock the head node, right? Unlike previously where we locked the entire linked list, we lock the head node. Let me just draw this out quickly. So let's say we want to add B over here and we have this linked list. Here's the head, there's the tail, and here we have A and C. The letters A and C, these are just placeholders. These are actually, like I said, we're using this as a key. This block over here will represent the key, and that will show the order. It's not going to actually be the payload or the item within the thing. So yeah, so like I said, we lock the head node, which I've already indicated on the diagram. I lock it there, and then next we say node.pred is equal to head. So go here, pred is equal to head, predecessor, and then we enter the try finally block. So then we say node car is equal to predecessor.next. So you say current is equal to predecessor.next. And so far so good, nothing too complicated. Then we actually lock this one. Once we have this, we lock it, and let's just get this lock image there. So yeah, we lock that. Let me put the lock on the other side just to be consistent with it being on opposite sides. And then try while current key is less than this key. So while A is less than B, do this. So within the order of the alphabet, A is in fact less than B. I guess maybe if this is confusing to anyone, we could just say we have 1 and 3 in the linked list and we want to add 2. Is 1 less than 2? Yes, it is in fact less than 2. So we enter this while loop and then we say predecessor.unlock. So now predecessor.unlock. The reason I'm not deleting it completely is because then I would have to redraw it and I don't feel like redrawing it every time. So predecessor is equal to current. So this moves over here. Let's just shift this up so there's space. Move that over there, and then we say current is equal to current.next, and then that moves there. Then we say current.lock. So then it's just going to, oops, every time that happens, bro. Okay, then we lock it, and this is the situation we have now. So cool, everything's done. So now we do the comparison again, right? We go back to the top of the, oh no, we go back to the top of the while loop, and then we compare current key is whether the current key is less than that key. We check is 3 less than 2. No, that's false. And so now we would have to exit the while loop. So once we've exited the while loop, we check whether current key is equal to key. This is much like the previous example with the coarse-grained synchronization, where we still this is literally just how the add block is going to work in every situation, because the add will return false if the node or if that item already exists in the linked list. Let's just write that down. Item already exists. But in this case, the item does not exist, and so we're going to just continue. And says node new node is equal to new item. So now we just create a new node, and then we put this in there, and then we say new node dot next is equal to current. So here this will be equal to current, and then predecessor dot next is equal to new node. Predecessor dot next is equal to new node. And let me just redraw this so that it's neater and so you can see how the linked list looks now. Okay, something I changed was I accidentally had this tail pointing to something, but it's just now there. But yeah, so I've redrawn the linked list after adding that, and then it returns, the function will return true, as it says over here, and then finally current will be unlocked, right? And then predecessor will be unlocked. Now I hope this makes sense to you. And you may be asking yourself, why do we employ this hand over hand locking? So now you've seen it in action. Now let's actually think about why. So consider the case where we have the following configuration. Let's say we have this situation where we have thread A working, thread big A working. Actually, maybe I should not use that. Let's just use numbers. Thread A working on node with 1, the node with 1, this one is working somewhere else, right? Thread A has locked this node, and now thread A wants to possibly either traverse the list or add something, but that's not too important at the moment, what exactly thread A is doing. All that matters is that thread A is not using hand over hand locking or lock coupling. So now what will happen is that, what could happen is that thread B or another thread could come, and what if thread B removes 2? So that would mean that 2 actually gets removed logically from the list, and so it gets removed. My apologies, I actually have it in the wrong order, sorry. What happens is that A wants to go from 1 to 2, and so what it does is it lets go of this lock first, and then somehow some thread, let's just say thread B, removes 2 from the list, right? And so it removes it, and now thread A can't actually lock anything, and so now it's unsafe. You can see that there's a problem now, because A was trying to get the lock to 2, but now it has been removed, and so even if it does get the lock here for this particular one, it could still possibly have a problem. Or it's, in general, you can just see that it is clearly unsafe, and it's better to rather just allow A to control both, and then let go of the predecessor. So it has both locks, and then it will let go of that one, and then it will try to get the next lock. So I hope that explains it. Now onto the actual removing function. With removing, what's important to note is that we also have to hold on to 2 at a time. We have to hold on to 2 nodes at a time, and the reason for this, you'll see the reason for this. So let's actually have a look at the code. Let me just draw it out quickly. So I've drawn it out, and we start as usual by, actually not as usual in this case, but we start off by setting the predecessor and the current to null. So let's just have them here, and they're both pointing to null. So then we set, this is the part that's usual, we set key to the one we want to add. So let's say in this case we want to remove that. So we want to remove 2. So this is the node that we're planning on removing. Then we enter, actually first, before we enter in the try block, we lock So let's just indicate that by putting that little lock there, and then we enter the try block. Then we set the predecessor to the head, and we set the current node to the predecessor dot next. So we set that to this, right? And then now we lock. This is again the hand over hand locking kind of thing, right? And here we have a nested try block. We have another try block inside. So now we enter that try block. Currently, in case you've lost track, we're over here, and we compare. We say, is current key less than this? So is 1 less than 2? Yes, 1 is less than 2. So we enter this while loop, and we unlock the predecessor, and then we set the predecessor to current. So let's just move that there. And then after that, we set current to current dot next, and then we lock that one. So let's just lock that, and then boom, cool. Now we check again, is 2 less than 2? I.e., is the current key less than this key here? Is 2 less than 2? No, 2 is not less than 2. So at this point, it would exit the while loop, and then we would go into this check over here. We say, is 2 equal to 2? Yes, 2 is in fact equal to 2. So that means we found the node that we want to remove from the linked list. And so now we're going to set predecessor.next to current.next. So we're going to take this, we're going to actually set it to here, set it to point to there. And then at this point, we return true. So we've removed this from the linked list by making nothing point to it, and so Java's the garbage collector will obviously just remove this. So yeah, let me just redraw so you guys can see how the linked list looks now. So here's the linked list, and here's the current node. You see over here in the finally block, the current gets unlocked, and so we left with this situation, and then this also gets unlocked. So now you're possibly wondering to yourself, okay, so what was the point of locking this one and this one at the same time if you're just going to remove it? And that brings us to this situation over here. You have to hold the lock of both the predecessor and the current node when removing, because you could run into a situation like this. So let's say that TA is trying to remove T big A, is what I'm going to call this because this is capital A, this is a small a, is trying to remove node A. Now it will, let's say it has the lock here. I'm just going to denote the lock by an L. So it has the lock over there, but T big B has the lock over here. And so if you try to remove A from the list, and then if you try to remove A from the list, what will happen is that this thread over here will set the head's next field to here. But then what will happen is that this one, TB, when it tries to remove B, it's going to set A's next field to C. Okay, in this case, actually, it mentions a C, but I actually don't have a C. So I'm just going to say it makes it point to the tail. And so what has happened is that we've actually only, if you look at how the thing is connected, B is still inside the linked list. It's still reachable from this point, right? And now we've actually failed in doing what we wanted to do. Hence, we need the hand-over-hand locking. So let's just draw what it should look like. Okay, so the way that it would work is that A would lock both, thread A would lock both nodes A and B, and then it could just simply go and make this head point at the next one, and then this is removed from the linked list. And then what will happen is that B will have its opportunity. A will let go of the lock, of course, then B will lock thread B, that is, and then it will actually, it has to start from here to here. It always goes from left to right, right? If you don't go from left to right, that can cause deadlock. So I know, sorry, my apologies for drawing it in the wrong order. It should actually go from left to right. So yeah, now it removes B by making the head pointer point to the tail, and now B is removed, and then it lets go, and now it's successfully removed both nodes from the linked list. So now you have to always acquire locks from the same order. What I mean by that is that it always has to go from the head towards the tail. And the reason for this is that you could end up getting a deadlock, right? Let's say you just have this situation over here where some thread A and some thread B, or let's make B red, are trying to lock from opposite sides. A locks this one, that one locks that one, and sorry, A also locks that one. Now B locks the tail. Now B is waiting for this A to unlock here. A is waiting for this one to unlock here. And I'm sure you guys can see there is now a circular wait. And so now we have deadlock. I hope this clears up the whole thing about fine-grained synchronization. And I hope to catch you guys in the next video. Thanks for watching. Please like, subscribe, share, etc., etc. All those other things. Now I sound like a real YouTuber, but yeah.